In class so far, we have learned that systems receive an input signal and produce an output signal. The output signal is also called a response. For example, a system like a car might receive as an input a signal from the pedal and produce as an output the car's velocity. Or a system like a spring might receive as an input position of the bottom and output a signal that is the position of the top. We learned that many or most systems can be categorized into just two different kinds of systems: first order and second order. For example, the car converting the angle of a pedal into a velocity was categorized as a first order response, while a spring mass damper system was categorized as a second order. We learned that systems of the same type behave or respond in the same way. All first order systems have a response that is defined by their time constant, while all second order systems have a response that is defined by their natural frequency and by their damping ratio. By knowing just these few simple characteristics of a system, we can predict many important aspects of the system response to a few standard inputs: the impulse, step, ramp, and sinusoid input. In the labs for this first part of class, we did many activities related to modeling systems experimentally. We did this by putting in a standard input like a step or a sine and measuring the output. This type of modeling is also known as empirical modeling. Empirical is a word that means based upon data or measurements. Empirical modeling is based on numbers that we measure during an experiment. In the second part of this class that we start today, we are going to begin looking at the mathematical underpinnings of systems. We are going to see exactly what, mathematically, makes a system either first order or second order. We will start to see how systems can be modeled mathematically and how parameters like the time constant, damping ratio, and natural frequency can be found or at least approximated without doing an experiment. This can be very useful when we are designing a system so that we don't actually have a system to test experimentally. Or if we have a system but we don't want to risk damaging it by doing tests on it. We can even determine from the equations whether or not a system has the properties of linearity and time invariance that allow us to predict the output to any arbitrary input. This type of modeling is known as analytical. Analytical modeling isn't based on an experiment. It is based on mathematical derivations. These mathematical derivations are based upon things that we refer to as first principles, such as Newton's laws or Kirchhoff's laws or the laws of thermodynamics. We start with these basic principles and derive equations to model the system. Both empirical and analytical modeling methods are important, and they each have their own strengths and weaknesses. Let's start with empirical methods. Empirical methods are as accurate as your measuring equipment and your ability to control the experiment. For example, in lab, we used the empirical approach to model the Slinky and to model the little electric car. We used our eyes and a stopwatch as measuring devices, and we didn't have very good control over the experimental conditions, such as when the little car started its movement. So our modeling results were not very good. We could only approximate the system behavior. We could see from the response whether the system was first order or second order, but we had difficulty getting accurate measurements for the time constant, the damping ratio, and the natural frequency. We also used the empirical method to model the motorized potentiometer slider. In that lab, we used an oscilloscope to measure, and we used a function generator to control the input, so our results of modeling were better. Empirical methods of modeling are especially useful in a couple of particular cases, such as when the system is very complex. And this approach is good when you have the system physically built and available to use in testing. If you can do a good job of controlling the experiment with the system and do a good job of measuring the results accurately, empirical modeling can be much more accurate than analytical methods, with less work involved in deriving equations. Analytical methods also have some benefits that you don't get with empirical methods. For example, you can use the analytical method without actually having the system. This is particularly a big pro when your goal is to design the system before building it. Also, analytical methods can give you some insight into the system behavior that you don't get with empirical methods. By having equations that define the system, you can predict the behavior of the system in ranges of inputs that you haven't tested or cannot test. Analytical methods can be much more accurate in cases where you can't do an experiment that is very well controlled, or where you can't measure the output very accurately. This might happen if your system is, say, very large or very small, or maybe the system that you are trying to model is being used in production and you can't take the system offline for enough time to do an experiment. Or perhaps performing an experiment would be dangerous or might risk damaging the system. Now, the biggest drawback of analytical methods is that you generally have to make a bunch of assumptions and simplifications in order to do the modeling, so your results might be too inaccurate for what you need. Typically, the best approach to modeling a system involves using both approaches. We first model the system analytically, making whatever assumptions we need to make. Then, we'll use the analytical model to predict the system behavior to some kind of input. Finally, we'll use the actual system to do an experiment. We'll give the system an input and measure how it responds. We compare the actual output of the system to the predicted output from the mathematical model. If the two outputs don't agree very well, then we know that we either did something wrong in our experiment. For example, maybe we didn't control the experiment well enough. Or maybe our measuring equipment isn't doing a good enough job of measuring the output. Or perhaps we made too many simplifications in the analytical derivations. Or perhaps some of our assumptions that we made in the analytical derivations are wrong. We then know to go back and find the error. In this part of class, we're going to be focusing on analytical system modeling. In these videos, I'm going to start by giving you two examples. We're going to analytically model these two examples, and then we'll look at our equations and see what they tell us. In order to start looking at how systems can be modeled mathematically, that is, analytically, we need to start by thinking about what our goal is. We want to come up with an equation that defines how a system converts an input signal into an output signal. For example, we might be looking for an equation that tells us how voltage of the little electric car becomes the velocity of the little electric car. Or we might be trying to figure out how your car converts a pedal angle into the car velocity. Or we might be trying to figure out how an RC circuit converts voltage on the left to voltage on the right. Because we are trying to figure out how one thing that changes over time, the input signal, becomes another thing that changes over time, the output signal, we would expect that our modeling operation will require using differential equations. We want to find a differential equation that has the output on the left side of the equation and the input on the right side of the equation. Let's take a look at the first simple example, a Slinky. Remember that when we're modeling a Slinky, we're not really just modeling a Slinky. We're modeling any system that can be represented in this way, such as a suspension system or a bridge. The first step of the analytical modeling process is to draw a conceptual drawing of the system. In this case, our system appears to be super simple. It is just a spring with a top and a bottom. But we have to be careful about the simplifications and assumptions that we are making as we go. The Slinky isn't really just a spring, because the conceptual idea of a spring that I've drawn here has only spring effects. It doesn't have any mass or any damping. On the other hand, we know that our actual Slinky does have mass. After all, a Slinky isn't actually weightless. The mass of the Slinky is distributed all along its length. Now, here is where we will make our first simplification. We will assume that the mass is just attached all in one location at the end. This isn't exactly right, and we might find out in the end that this is too big of a simplification and we would have to go back and fix it. But for now, this simplification makes our task much easier, so we're going to try it and see how it goes. The process of deciding how many simplifications are okay and what simplifications are not okay is a matter of trial and error and experience in modeling. This is why it's so important to use both analytical and empirical methods. Here, we've decided not to make the simplification that the Slinky has no mass. But we have decided to make the simplification that the mass of the Slinky is all attached in one location at the end of the spring. To find out which of our simplifications are okay to make and which simplifications are not okay to make, we have to derive the equations with our simplifications, use the equations to predict the output of the Slinky, and then use the actual Slinky to see if our predicted output matches the actual output of the system. If they don't match closely enough, then we know that we've made too many simplifications, and we have to go back and make our conceptual drawing of the system more closely match the actual system. Now, the Slinky doesn't have an actual damper attached to it either. Incidentally, if you've ever wondered what an actual damper looks like, it looks something like a pneumatic cylinder, which looks like this. If you'd like to see a damper in real life, one good place to see that is on a mountain bike. A mountain bike suspension generally consists of a spring, which you can easily identify, connected together with a damper, which will look a little bit like this, a cylinder. Next time you're in some place that sells mountain bikes, go take a look and see if you can find the spring and the damper in the suspension system. So our Slinky obviously doesn't have an actual damper attached to it. However, we know that the Slinky does have damping effects, because when the Slinky is oscillating after receiving some input, it doesn't oscillate forever and ever. The oscillations eventually die out. That's a clue to us that the Slinky does have damping effects, even though it doesn't have a physical damper. The damping effects are provided by the material that the Slinky is made of. So, in our conceptual drawing, we will draw a damper. Now, I need to label these things so that I can use these variables in my equations. The spring has a spring constant, and the damper has a damping constant. Once our conceptual drawing is finished, we move on to step 2, identifying the input and the output. Remember that the input and the output can be whatever you want them to be. We're trying to create a model that uses the input and the output that we are interested in this system. In this Slinky, I'm going to make the input be the displacement of the top, and I'm going to make the output be the displacement of the bottom. So I need to draw those things into my drawing. The drawing shows the direction of positive motion, and it also shows the position that is defined as 0 for both the input and for the output. Now, the output is typically represented with the letter Y. And since the value changes over time, since it is a signal, I will make Y be a function of t. The input is generally represented either by the letter X or by the letter U. You will see it different ways in different textbooks and technical documentation. For now, I'm going to represent the input by the letter X. Once we have the input and the output defined, we can move on to step 3. Step 3 is to apply physical laws. You have to pick which physical law you're going to apply based upon what type of system it is. Here, since it's a purely mechanical system, we can apply Newton's law. Specifically, I'm going to apply Newton's second law of motion, which says that the sum of the forces is equal to the mass times the acceleration. If this was an electrical system, we might apply Kirchhoff's law. If this was a thermal system, we might apply the laws of thermodynamics. In order to sum up the forces, I'll start with mass times acceleration. I'm going to write acceleration as y double dot. That is the second derivative of the position of the mass. I'm doing this because I'm trying to come up with an equation that relates y of t and its derivatives to x of t and its derivatives. Remember that what we're trying to do is come up with an equation that relates the input and the output together. On the right-hand side of the equation, I'm going to sum the forces on the mass. Here we have two forces, the spring force and the damping force. I'm going to ignore the force of gravity because the force of gravity is not related to the input or the output. I've defined the output here, y of t, as being 0 at the position that the mass is in when it is resting with gravity applied. So I'll start with the spring force. The spring force is in the positive y direction, and it's equal to the product, K, times the difference between the position of the top and the position of the bottom. You can check yourself with the negative and positive signs by imagining the system in some condition. For example, when x of t is positive and y of t is 0, the spring force will be pulling the mass up. So it should be that when x is positive and y is 0, that this whole force will be positive, that is, pulling the mass up. And we can see that that is true here. Also, when y of t is positive and x of t is 0, the spring force will be pushing the mass down. So this whole force should end up being negative. We can see that this is true. When x of t is 0 and y of t is positive, this whole force will be negative since y is subtracted from x. Now I also need to represent the force of this damper. The force of a damper is dependent upon the relative velocities between the top and the bottom. So we can write the damping force like this. Once again, we want to check ourselves to see if the sign is correct. If x of t is moving faster than y of t, then the damper will be pulling the mass up. So it should be that when x of t is greater than y of t, this whole force term is positive. And we see that that is true here. Similarly, when y of t is moving faster than x of t, the damping force will be pushing the mass down. We can see that this is correct. When y of t is greater than x of t, this whole term will be negative, indicating that it is pushing the mass down. Now, I can expand this to get the same equation in a slightly different form, like this. Note that the double dot indicates a second derivative, while a single dot indicates a first derivative. Now I'm going to rearrange this equation one more time so that I have the input on one side of the equation and the output on the other side of the equation. For now, I'm not going to try to solve this equation. For now, I'm going to move on to the next example, and we're going to find the differential equation that defines this other example. Then we'll look at the two equations side by side and see what we can determine about the equations. For example 2, we're going to analytically model a sliding mass. Do you remember this picture from earlier videos? This is the system we're going to model analytically right now. An object being pushed across the floor. Similar to example 1, we're going to start with step 1, drawing a conceptual diagram of the system. We're going to start by representing the chair as a single point mass. Now, similar to the Slinky, this isn't necessarily true. The mass of the chair is distributed throughout the chair. We're making a simplification here by saying that the mass is just this box with a single mass. Now, we're going to identify the input and the output of this mass, as well as any other forces that are acting on the mass. For example, we have a force applied by the person. I'll call this Fa of t. This applied force is the input. The output is going to be the velocity of the mass. I'll call that v of t. And I'll make a note that this is the output. Similar to the Slinky, we could have picked many aspects of this system to be the input and the output. We could have chosen the output to be the position rather than the velocity of the mass, for example. We choose the input and the output to be the thing that we are interested in. Now, before we move on to derive the equations, we need to make sure we've drawn into this picture all of the forces that are applied to this mass. So there's one other force, which is the force of friction. There's also a gravitational force pulling the mass down, but that force I'm going to work into the force of friction. Now, let's sum the forces on this mass. We'll say that the mass times the acceleration of the object, that is mv dot of t. Notice that I did not say the second derivative of position, because here position is not my output, the velocity is the output. So the left-hand side of the equation has mass times acceleration. I need to sum the forces for the other side. On the other side of the equation, I have the applied force. This is the input. I also have the force of friction, which I'll say here is equal to mu times mass times gravity. I don't need to do any other rearranging of these equations because I already have the output on one side of the equation and the input on the other side of the equation. So I'm finished with this derivation. Now let's take a look at our two equations together and see what we can notice. Here I've written the two equations that we came up with underneath the title of the system that it represents. I want to point out a couple of key aspects of these equations that you should notice. First of all, notice that with the spring mass damper system, the left-hand side of the equation includes the output, the first derivative of the output, and the second derivative of the output. In the sliding mass, all we have is the first derivative of the output. There is no second derivative of the output included. This is what we mean mathematically when we call a system second order or first order. A system that only has the first derivative of the output in the equation is called a first order system. A system that has the second derivative of the output is called a second order system. This is how we can determine whether a system is first order or second order without doing an experiment. When we derive the differential equations of the system analytically, we can look to see whether only first derivatives are involved or whether there are second derivatives, and that defines whether the system is going to have a second order response or a first order response. So what else can we find out about these systems just from their equations? We can tell whether or not the systems are linear. Remember that linearity is related to whether or not the superposition principle applies. If a system is linear, then the superposition principle does apply. So what does this linear concept mean in terms of our equations? Notice that in these equations, there are no places where the input or the output or any of the derivatives are squared or to any other power. These two equations both are the sum of constants times the input and output signals and their derivatives. Mass is a constant. Damping is a constant. The spring constant. All of these things are constants times either the input or the output or the derivatives of the input or the output. There are no squares or cubes in any of these variables. Similarly, in the sliding mass equations, all of the parameters are constants, and the variables are not squared or cubed. Also, there are no sines or cosines of the input or the output or any of the derivatives of the input or output signals. This is the mathematical basis for a system being linear. If we see that our equations are just constants times the input, the output, and the derivatives of the input and the output, then we know that the system is linear and the superposition principle applies. Finally, there is a third characteristic of the system that we want to notice about these equations. Notice that the variable t, which represents time, only appears in the functions of the input and the output. This is true in both of the equations. Time never appears as a variable by itself. This tells us that the systems both have the characteristic of being time invariant. Remember what the property of time invariant means? It means that the time at which an input is applied only has an effect on the time at which the output starts. It has no other effect on the shape or characteristic of the output. Mathematically, time invariance can be seen by noticing that time does not appear as a variable on its own. If the system was not time invariant, for example, you might have the friction force over here appearing as mu times m times g times time. This kind of a system would not be time invariant because time appears as its own variable, not as a part of the input and output functions. So in this video, we have learned about what analytical modeling means and the pros and cons to analytical modeling as opposed to empirical modeling. We've also seen that analytical modeling involves some assumptions and simplifications, and you have to be careful about the kinds and amounts of simplifications and assumptions that you make. We've also seen two examples of analytical derivations of differential equations, and we've looked at the equations to see three of the system characteristics that we can see from the differential equations. We've learned the difference between a first order and a second order system in the equations, and we've seen what it means for a system to be linear and time invariant in the equations. In the future, we're going to be seeing how these equations can also be used to determine system properties like the damping ratio, the natural frequency, and the time constant. But for now, we'll stop here with these three characteristics of systems that can be seen from the differential equations.